Okay, so for this lecture, I just wanted to focus a little more on something that I brought in last time. And so we need an emblem for this lecture. The key thing is it's literally possible to use brute force and make assertions about something having solved a problem in the real world. The question is that if you have a contest where there's a sequestered test set, but individuals are submitting many entries, is there some possibility that the test set no longer is purely test? The feedback effect that you get is creating some overfitting. Okay, what I want to do now is just take you through enough of the basic machinery so that the little emblems that I put up for this lecture will have a clear meaning to you. This convergence of the arrows at a node here means that we're summing up all of these input values times the weights and producing just that simple dot product. Now we can create multiple layers, and I'll just remind you that in each case what's happening is there's a linear combination coming in, producing an affine result on the inputs. A key thing that I want to mention is this is just motivational. It's not what people actually do. What they actually do is stochastic gradient descent. The structure that we're talking about can be traced way back. I would encourage you to look at a survey paper by Jürgen Schmidhuber about the history of the subject. Has a staggering number of references in it. At the same time, when the Olshausen field work was done, it was recognized that much of what Olshausen and field were finding by learning from data, normally the math would suggest to you that there's a nesting property and you should see a monotonicity of the achieved performance. During training, you're separately recording the mean of each input and the standard deviation of each input, and then you're going to be able to know how to do a standardization of the data using that extra little piece of information that's stored somewhere separately. Another thing that's been learned is that the filters that are being learned in these convnets at the first layer are somewhat problem independent. In some way, getting the same result you ought to be able to get by an unsupervised problem, but we don't know what that unsupervised problem is. We don't really understand why this is emerging. Each one of these little squares here is an image, and so this is sort of a rendering of a little image patch. So as you can see here, there's 25 types of filters, and then each filter has a spatial footprint. So it's learning a series of coefficients that are in some way analogous to the grandmother cells that we showed pictures of neuroscience having discovered in recent years. What is the feature in this deep net that responds most strongly to the prototype frog? This was the diagram that I put up as just an emblem of what we were trying to accomplish in this talk, just to let you understand what it means when I say that the standard way people talk about these networks is they go from pixels to edges to parts, so on and so forth, and then the invariance at the low level and the object-specific nature at the high level. Thanks for your attention.